Hi everybody, let's refresh our JK flip-flop, and this one I'm going to use the PSPICE to explain to get a better pictures. Well, when you take a look at the JK flip-flop, what I have here is like I have 47107 as the JK flip-flop, which I got it from PSPICE. You just type it in 741 and then 07. This is what you have in front of you in the JK flip-flop. And what I'm going to do is I'm going to show you how the JK flip-flop works, and then you take a look at the truth table. You have input JK and you have output. So for this one, I will assume that ignore the clock. Okay. For this one, um, it's going to work on the trailing edge of the clock. So this means you change the output status. Can be either from 0 to be 1 or 1 to 0. So from the rising edge or the leading edge, okay, it's not going to affect your output. So the way it works is that when you have input of j and k to be 0, so this status still keep it to be your q. So I'm gonna put this one here as the q, and this one is to be q prime, and that's why the mean output status still doesn't change. So this is what we call latch. And then when the input jk becomes 0 and 1, this is going to give you a 0 for q, and of course this one q complement is going to be your 1, sorry, and this is going to be what we call to be your reset. And for jk input to be 1 and 0 here, you have our q is going to be 1, and of course your q complement is going to be 0, and this is what we call our set. And for this one, our jk input become 1 and 1, and your output is going to show up as the q complement, and this is q, so it's going to be the opposite of the digital logic of the previous stage. For example, if you have the previous stage of the q here to be 0, so this one gonna change to be 1, and this is what we call our toggle. Okay, so this is what is the truth table of the JK flip-flop look like. Now let's get back to the JK flip-flop to give you a better idea. What I'm going to do is that I'm gonna break the signal, which in case I have J, K and clock, and also clear. And for the clear signal here, it's gonna work by a digital logic 0, so it's gonna set everything, I mean your output here, to be 0. But if you are, so that's why I set the clear signal here to be high. We simply set up, sorry, I did attribute here, so that's why I have on time but never have like off time, so it's always have a digital logic to be 1. And for J, K and clock, I show in their waveform diagram here. So this is my J, this is K, and this is clock. For the clock, I have the period to be half of the input K, and the input K, I have the period to be half of the input J. Okay, just to showing purpose. And the way I set up the clock period, what I did is I go to attribute, I set on time to be 0.5 microsecond and off time to be 0.5 microsecond, or the period is 1.0 microsecond. So that means I'm going to set the K period to be double of the clock signal period. So I want this one to be the period of 2 microseconds. So it's very easy. So I just set up this one to be sorry, I made it double. This one's supposed to be what? 1 microsecond. You can do anything what you want. And for J, it's going to be double period of the K input signal. So I have this one to be 2, right? And the period to be 4 microsecond. Okay. And for the setup, I set up the transient time here. Since you want to see the whole waveform, I have the maximum period to be what? 4 microsecond, right? So 20 microsecond is more than enough. Now I go to simulate, and I want to show you the corresponding waveform. So let's start with adding up our J input waveform, add up the K input signal waveform. So the periods become half of the input signal of the J input. And let's go to the clock. And that should give you also the half period of the K input signal. And now I want to see your output. So my output is at the U1A Q, right? So this is have a U1A and Q. And then now I can explain to you what happening. I mean, and how the JK flip-flop works. So let's turn the cursor on here. Alright, as I mentioned earlier, okay, back again. So you take a look at the start from different inputs of J and K, and then compare your output to see the output from the PSPICE. Now you start from let's say 0, 0 first, right? Okay, let me write down here. I have J, I have K here, and you have 0, 0. And what is your Q? And your Q prime. So this one is latch, right? So it still become a Q prime, and it's going to work on the trailing edge of the falling edge of your clock signal. This is your clock signal. So you take a look at the case of J and K becomes 0 and 0. So let's take a look at this here. This is your 0 and 0, right? But we don't have the falling edge yet. So let's move to whatever we have the falling edge. Here I don't have any falling edge at all. So in the case of J and K, it's 0 and 0. Okay, so it's my mistake. So it's better to get the larger period of K and J. Alright, so sorry about it. I will get back to the output waveform again. Let's go back to the setup. Sorry. So this is, we have the period is what, 1 microsecond, right? So let's make this one to be full microsecond. So it's not so difficult to change. I put this one to be 2 and I put this one to be 2, right? And then back here the period's got to be your 8 microsecond. So I change this one to be your 8 microsecond. Now I can do our simulation again. Let's start with the J and go to K, and then let's pick up the clock signal, and then let's pick up the output here. Alright, let's take a look at the case of J and K, and then Q, and then Q prime. When we look at the falling edge of the clock signal, so let's take a look at this one, 0 and 0. Do you have any 0 and 0 somewhere? Alright, take a look at this region here. You have 0, 0, and the falling edge here. You can see that this is your clock coming in, right? And this is J1, this is J, and this is K. So what happened? You have 0, 0. It should give you the previous stage, right? I mean, to be the same. So before you have the falling edge, the digital logic of your Q is 1, so it stay at 1. It's to be the same, right? Okay, so now let's take a look at the J and K. In the case of 0 and 1, right? This should give you what? Reset. Give your Q to be 0, correct? So where is J become 1? Sorry, J becomes 0 and K become 1. So this is 0 and 1 here in this region, correct? And for the falling edge here, you can see that your output change the digital logic from 1 to be 0. So this is what we call reset. And what about 1 and 0 here? 1 and 0. Look at this region here, because J is 1 and then K is 0. So for the falling edge, you can see that this is going to be set. So they change the digital logic of Q to be 1, exactly according to the truth table. And for the last one, for J and K is what? 1 and 1. This is toggle, right? So you should change this one to be Q. Sorry, the state here should be a complement of Q, and this simply become Q. So let's take a look at the case 1 and 1. So take a look at this region here. This is 1 and 1. This is the falling edge, right? So the previous stage of their Q is 1. So when you have the falling edge coming in and JK is 1 and 1, so your output is turned out to be your Q complement. So that's why it switch from 1 to be 0. Alright, so this is how the JK flip-flop work by looking from their PSPICE simulation. Now let's go to for some design. Let's take a look at the design of 4-bit Ripple coder. This is one application using our JK flip-flop and asking you design a circuit that produces true output equally if the count reach the binary equivalent of 12. Neglect micro timing effects and assume A is the LSB or least significant bit. Okay, what does this mean? It means that this is what the counter, start from number. Actually, this one start from 0, right? And then come 1, increasing by 1, 0, 1, 2, 3, 4, 5, 6, 7, 8. And this is the input according to DCBA, when A is the least significant bit and D is the most significant bit, right? Well, I will show you the way how to design, and probably many people know about that already. How to design the ripple counter. The toggle mode of JK flip-flop. What does it mean, toggle mode? The toggle mode is mean your Control C. Right, sorry, computer have some problem. So the way we did is we used the 4 JK flip-flop because we need 4 bits, right? DCBA. And then when we talking about using the toggle mode, it mean you're going to connect J and K together, all of them, right, like this. And also let's cut this away first, right? Control X and then Control V. I put it somewhere here, and then I Control W just to connect the wire, and then let's move this together. Okay, so we're going to connect all J and K of the JK flip-flop all together. This is how you design the ripple counter circuit, and I will explain to you how this one is work. And this one are going to connect to the digital logic high, because you want to toggle, right? So the input digital logic has to be high, so it's the same thing as the signal get into clear pin of JK flip-flop. Okay, if I check this one again, you can see that you never have like off time, so only on time, right? Off time to be 0. And then the way they do is they connect your Q to the clock of the next JK flip-flop or the neighbor JK flip-flop. So you repeat this again and again for all of JK flip-flop here. And then this is going to have your output QA. I can change this one to be your, this is the least significant bit, right? Least, and then this is the most significant bit. So let's put this one as the B. Get B, and then let's put this one as the C, and let's put this one as the D. Oops, sorry. Alright, now you already have our connect all together, but also the clear pin, you connect them together. Alright, and then you are set. And for the clock signal here to have the clock coming in, I simply put the clock into the first stage, or the least significant bit, and I don't need J here, I don't need K here. Okay, so this one is going to be your QA, and this is QB, and then QC, and this is QD. Okay, this is how it's going to work according to the waveform diagram here. You can see that the lower or the falling edge is going to trick your output. Let's get back to the circuit. When the clock coming in, you can see that this is in the toggle mode, right? And your output simply is going to be change according to the falling edge of your clock signal, all of them, right? So just to make it easy to understand, you don't have to confuse about anything else. When your clock signal coming in, when you have like falling edge coming in, and this is used to be the digital logic 0, and then it's gonna change. You take a look at this one, QA is going to turn out to be from 0 to be 1, right? And for QB, this is the become what 0, and it cannot change the output stage until the falling edge of QA is coming in. And this one do the same thing here. When you have the falling edge is coming in, your QA is like change. Sorry, let's start over again here. This is your clocks, and you have the signal coming in. Your QA, you have to start from reset, which is 0. It's not going to change anything until the falling edge is coming in, right? And which is the toggle mode. Your QA is simply going to be your QA prime or QA complement, which is become the opposite logic of the previous digital logic. So it used to be 0, so now it's turned to be 1, and it's going to wait for another falling edge of your clock is coming in. So it's going to stay there until your falling edge is coming in. Do the same thing here. It's going to switch around, right? It starts from 0 and it's changed to be 1, and then it's back to be 0. This is how it works. And it's keep it's repeat itself, you know. Now it's for QB. It's for easy to understand. This is your QB, right? Your output QB here is going to change when the falling edge of the clock, which is QA, is coming in. So what you need to take a look at this is like you look at the falling edge, and it used to be 0, right? Start from 0, and then when the falling edge is coming in, it change your output stage to be 1, and it's keep repeating. So that's why this is what we call the ripple counter, and this is the way how to connect the JK flip-flop to make the ripple counter. Okay, and then you can see your Q of 1 A, B, C, D. If I hit the simulate here, sorry, duplicate name of clear, or it's not allow you to use the same name of the PSPICE. I'm not sure if I can change this one clear. I have problem with this. What about if I don't use clear at all? No, it's not allow you. Well, in this case I have to use this one. This one have to be change the newer name, right? And change this one to be clear 4. That's it. And then this is the clear 3, right? And this has become clear 2. Okay, doesn't matter. Now let's do our simulation again. Nups. Let's see what happened. Duplicate name clear, because this one is itself. I don't know what. It's not allow for you to change this one at all, so you cannot use this is duplicate name, so that's problem. Alright, but this is the idea how the ripple coder work using our JK flip-flop. And if you take a look at this one here, will produce a true output if only if the count reaches the binary equivalent to 12s. So the way you do it, actually this is 0 and 12 is supposed to be 13, right? So in this case, that means you need require your output of what? QD, QC, QB complement, QA complement, OR them together using the 4 input OR gate, and you will get your output. So this is how it works. So what you need to do is you require 0, 0, 1, 1, right? So what did you need to do? This is the 0, 0, 1, 1. So you need to look for 4 input OR gate. This is not an OR gate, so I need to look for I don't remember what is the number. This is the NOR gate. Oops. Nope, I don't have it straight here. But it doesn't matter. So you have like 0, 0, 1, 1, right? So what you need to use, you need to take the QA complement, which is the Q bar, and then QB complement, which is the QB bar, and then you pick up just Q, C, right? And then QD, and then R them together to give your output as required, because they say like the true output if only if the count reaches the binary equivalent to 12, and you take a look at 12. So it's right here. This means you require QA to be 0, or you take the Q bar, QA bar, right? QB bar, and QC, QD, and then OR them together. Okay.